So it means that that liquid has a temperature, which is defined by the boiling temperature. For atmospheric pressure for sea level, it's 100 degrees Celsius, and thereby you know also the pressure, because water boils at sea level at 100 degrees. So therefore, that sea level pressure it's the sea level pressure, which is 14.69 psi or 101.3 kPa. So by knowing T, you know P, and by knowing P, you know T for saturated steam or water, for any saturated liquid. Okay, that's important. All right, so I'm going to go ahead and get going over here. Let's see. All right, so again, if you know, so what is it? Let's see, did I, oh. All right, so again, this is important here, important attribute of saturated liquid. So let's go ahead and write this down here. This is saturated liquid. All right. So if you know the pressure, you know the temperature. If you know the temperature, you know the pressure. And I wonder if I still have my tables. Homework solutions, homework solutions. Let me go bring the tables up. I think I have. So if you go to, and I forgot to put table, one of your sections doesn't have tables. Let me go to contents. See, let's go to this section here. And then you go to content. And okay, so this is the section that has the tables. So if you don't have a textbook, you can always go here to Beachboard and go to tables and open up basically the appendix, the back of the book. And we're going to need this for our class right now. So actually, I didn't download this. Should I download it? That's fine. Yeah, let me download it. Okay, a little easier to deal with when it's downloaded. All right, so the tables, the saturation tables for water, for example, is tables A4 and A5, and that's in the appendix of your book. You can see that when you look at this table, saturation water tables, is you can see that we have, oh, that's weird. All right, so if you know temperature, you know pressure. All right. So for every unique temperature, so it's, for example, 25 degrees C for water will boil at 3.1698 psi, or it's kPa. Sorry, it's kilopascal. So we know that this only applies for saturation. It only applies when you're boiling water and you haven't boiled it all the way yet. Okay, so therefore the sorry guys, I want to make sure I get my messages here. Yep. All right. Therefore, these are not independent. They're not independent property. This is not two independent variables, right? P and T are dependent for saturated. And remember, whenever we define a state, remember I went over the states 1 through 5, the conditions when we were taking water from boiling, from cool water all the way to superheated vapor. States are defined by, you have to have two independent properties. In other words, you have to be given a temperature, and in this case, the fact that it's saturated liquid. So if you're given the temperature and the fact that it's boiling, so if you're told, I'm boiling a pot of water, the temperature is 90.5 degrees Celsius, then that defines a state. I got two independent properties, but if I say that I'm boiling water, it's at 100 degrees C and it's at 101.3 kPa, those are dependent properties, and you need to find another. Well, you are given, actually, in that situation, you're told boiling water, so therefore you are given the fact that it's a saturated state, and you can use that table that I just showed you, this one, and you can thereby solve any problem with this. You got everything. You got those two. You got a temperature, and you got the fact that you're saturated, or you might be given temperature, and you might be given a specific volume. So if I said I have a temperature of 60 and I have a specific volume of 0.0256, find any of these values: internal energy, enthalpy, entropy. I'll show you how to do that, because today we only really talked about, up to today, we only really talked about F and G are basically our sub-indexes. F means the liquid side of that of the saturation, and G is the vapor side. All right. So then I'm going to show you everything in between today. All right. Let's go. Let's go. Let's go. Let's go. All right. All right. Let's see if we have room here to write. All right. So now we're going to talk about quality. And we give it basically the variable X. So what is quality? So quality is, let me give you the definition. I want to make sure I have it all written here. Basically, it is the mass of the vapor divided by mass total for a system. So for example, a system would be this right here, right? Inside here, there would be the system. So the mass of the vapor, so this is just the vapor part, this pink section here, divided by mass total. So mass total is basically the liquid and the vapor. So right, so you got mass total equals mass. So what we do is we give F for liquid plus mass of the vapor, right? So that's your mass total. So if I add the two masses, I get my mass total. So this is quality here. This is quality. And think about it, the thermodynamics was created because during the Industrial Revolution, people started to use to create things that operated with steam, for example, like steam engines, steam locomotive trains. But not only that, but shop equipment had steam engines, right? You can actually have a mill, a buzzsaw, industrial equipment that ran on steam. And so it was really difficult back then. If you remember, locomotive operators were engineers, and we still give that title to locomotive operators, though you don't really have to be an engineer anymore. But back then, you needed to be able to design a pressure vessel, right? You need to be able to know how much you can take this pressure vessel to, what temperature, how much quantity of vapor you had in a given container, and thereby knowing how much power or how much energy was inside the tank. And so you needed engineers so that you wouldn't hurt people, right? And so it was important. So the term quality came from that. The goal was to have high quality vapor, right? So therefore, you wanted mostly that mass to be vapor. That M total, which is the combination of the liquid plus the vapor mass, higher quality meant the higher vapor content, but as a function of mass, right? So that's where the index came from. So let's go ahead and write some other information here. All right, so let me show you something. I'm going to write volume is the letter V, and usually I put a little line here to designate volume, so that you don't think it's a velocity, especially when we start getting into kinetic energy and all that. So we're going to say the total volume is equal to the volume of the liquid plus the volume, again, little hash there, the volume of the vapor. All right, and thereby we know that the volume of the liquid is equal to m, the mass of the liquid, mf, times the specific volume of the liquid. Right, the specific volume is basically meters cubed per kilogram. Right, this is what we've been doing here all along, right? Giving you that's why we use specific volume. So the total volume is the mass of the liquid times the specific volume of the liquid plus the mass of the vapor times the specific volume of the vapor. All right. And all right. So then another way of writing mass of the liquid is to say it's the mass total, right, minus the mass of the vapor. So that's another way. So that this way we don't have to, if we do an equation, we can get rid of the MF, mass of the liquid, and just have it in terms of mass total and mass of the vapor. All right, so I'm basically coming up with the expression of how to solve some of these problems using quality. All right, so we have that. Now, let's see. So the total, all right, so the total volume, again, is equal to the total mass times the specific volume, the average specific volume. All right, so that's basically the average in here. There's inside here, yes, the vapor has its own specific volume, and the liquid has its own specific volume. But inside here, there is an average, right? And we call that specific volume average, right? And that's what this is giving us right here. You can stratify that. You can actually break it up into VF and VG here, but it's actually but it's an average, because it's really doesn't always separate like this. And even if it didn't, we need an average of the tank. So we call that total volume is equal to the total mass times the average. All right. All right. Now, so this is also equal to mass. Let's see. So mass of the total is equal to. Okay. Okay, just a second. I'm having an issue here looking at my. All right, so we can also say that the total volume is this, right? And we can say that it's instead of saying mass of the liquid, we can say it's mass of the total volume, or the total mass, minus mass of the vapor. And then this is all in your book, but I'm just describing it to you guys. And then this is the V sub F. Again, this is this equation over here, plus mg v sub g, right? And now if we divide by mt, so we go up here now. If we divide by mt, we get that the V average is equal to 1 minus x VF plus x times V sub g. All right, so we just divided by mt, and that gets to this that I just defined. Yeah, so this gets to this derivation here, and I guess I haven't really defined it, but x is also equal to mass of the vapor divided by mass total, right? Like that. So when we do that, we get this equation. And again, we got, since we have, actually we don't write mass of the vapor, we write mass. So we say x is equal to, since we have x is equal to mass g divided by mass, we don't say mass of the vapor divided by mass t. It's important that I should give you this correctly. Since x is equal to that, then therefore we say V average is equal to V sub F minus x VF. All right, when we multiply VF through. plus x Vg, right? So that's just multiplying 1 minus x through. And then finally we got, let's just go ahead and just say, we got V, so what's Vf? We got Vf. And if we have, we group the x's back, we say plus x. This is Vg minus Vf. Right. And then, but what we do is we substitute, instead of Vg minus Vf, we're going to say let Vg minus Vf equals this term here called Vfg. And therefore we have V average is equal to Vf plus x Vfg. Right. So that's our final take on this here. So this is how we find see if I can make this a little bit more clear. Go back to our lecture here. Maybe we'll do this one first. So this is how we find basically the V and under the curve, under the bell curve of the saturation curve that I just told you, that just showed you here. So let's see. Right. So for example, yeah, say you have a point here. Say you're given a temperature, and you have a quality. Maybe you were given a quality, or you say your quality is 0.5. Then you can go ahead and you can calculate the V here associated with that quality. This is so you can use the tables in the back of the book basically for anything associated with the curve, with the saturation, and inside the curve. All right, because what inside the curve designates its mixtures. So everything we've done so far was just basically using the pink portion of the curve, right? We said if you boil water and you boil it, all off, then it becomes vapor G. And but now we can determine these values here in the center. All right. Now let's see. It turns out that everything now in the appendix can be calculated the same way, right? So with using quality. So the appendix so this is just specific volume, but really the back of the book tables to solve problems, we use them to solve energy problems. So let's see. So I gave you specific volume, how to calculate specific volume given a quality, X. But you can also solve, if you want to find the internal energy, average internal energy, then it's the same calculation. And the enthalpy, it's the same calculation. All right, so you use the same format. This is kind of like almost like a rule of mixtures way of given the quality, you can find the internal energy and the enthalpy, and also the specific volume for any material that's within inside the bell curve, inside that saturated curve. All right, if there's any questions on that, let me know. We're gonna do some examples. Yeah, go ahead.
So U is, you said internal energy?
Yeah. Yeah, U is internal energy. So here it is here. And I haven't showed you in what situation you would need to use this, right? I think we did talk about a little bit about internal energy. It's basically associated with the temperature of a chamber. And so it's usually associated with a rigid tank, and then you take a fluid from one temperature to another, but was saturated fluid from one temperature to another. And this will be the energy associated with that in kilojoules per kilogram. Enthalpy we haven't really talked about. I'm going to describe that in a little bit. But it's like internal energy, but also now there's another part of internal energy. Now, what if you have moving fluid or moving surfaces, like we're moving the piston up, right? As we were going from state 1 to state 5, we maintain atmospheric pressure inside the piston, but the piston kept moving up, right? So the fluid that we were heating up was doing work. So the enthalpy includes that work that it was doing. I'll explain that in a little bit. And then there's entropy, which is chapter 6. I'll explain that when we get to that point. But yeah, this one's U, this one's H, and this is S.
And X always represents the mass ratio.
Exactly. Yeah, X is the mass ratio here. Yeah, it's the mass of the vapor divided by the total mass of the system, or vapor plus liquid. Okay, so what does that mean? All right, so let's go ahead and do an example here. So in the book, we have, let me go open to that chapter 3. Let's see, this is example 3-4. Let's see if it's true still. 3-4, yeah, I believe it is, 4 points. All right. All right, so let's look at example 3-4. So it tells us that, it says a rigid tank contains 10 kilograms of water at 90 degrees Celsius. Eight of those 10 kilograms of is in the water form, is in liquid form, and the rest is in vapor form. So determine the pressure in the tank and the volume of the tank. All right, so maybe this is a good opportunity. I'll copy this here, and don't disregard the we'll get to this next. All right. Okay, sorry, let me. All right. So so again, we have a tank. Just like it's shown there. And there's 10 kilograms in this tank of water. All right, so there's 10 kilograms in this tank of water. I'll just put it out here because I have to put a line in here. And then it turns out that there's a separation just as shown there, that there's actually a water line right there, and at the bottom we have water, and then at the top we have, I'll just say yellow for vapor, right? And the bottom has 8 kilograms, we said, is water, and then the vapor, this is in mass. The vapor is, therefore the vapor is, we were given it's 10 kilograms, so therefore the vapor has to be 2 kilograms. So I'm going to say, yeah, vapor. And then 2 kilograms of water. Okay. All right, so we're given that it's 90 degrees C, and the problem is asking us to determine the pressure in the tank and the volume of the tank. So find pressure of the tank, and then find the volume of the tank. So we're finding the pressure of the tank and the volume of the tank. Okay, so what we know that this is saturated. It tells us because we have two components here, right? We have this component and that component. we have liquid plus vapor. Therefore, this is saturated liquid. This is saturated liquid. All right, so that gives us that now we can use saturation tables for water to solve this problem. And if that in the back of the book is the tables are A4 and A5. All right. So A4 is when you're given temperature, which is what we're given. We're given the fact that this is 90 degrees C. A5 is when you're given a pressure. We're trying to find a pressure, so we won't use A5. All right, so let's go ahead and determine the pressure. The first one is the pressure. So let's go ahead and look at our tables. So here's table A4. I'm given a temperature of 90 here. And therefore I need to find, I wonder if I can highlight this whole thing. Oh yeah, I could. So I got 90, so therefore this is what I'm interested in. Right next, the column next to the temperature is the pressure. So therefore that is my pressure for that temperature. I got 70.183. All right. So pressure is equal to 70.183 kilopascal. All right. And then that's basically my final answer there. That takes care of that one. Now I need to find V, the volume. I got that one. Now I need to find V. All right, so V, to find the volume, we need to determine how is it that we determine volume, right? So we need to find V. And from the previous examples that I showed you, the written work, volume is equal to, there's two volumes here, right? There is the volume, and this is total volume of the vapor, and this is the volume of the liquid, right? So the total volume, so I'm being asked to find the volume of that tank. The total volume is equal to the volume of the liquid plus the volume of the gas or the vapor, right? And that is equal to, if you remember from the last, that's mf little v f plus mg little v g, right? And these right here are table values, right? We get these from the tables. So let's go back to the table. So little vf is the third column from the right, and the fourth column is little vg. So it's 1036 and 2.3593. So I wonder if I can just copy and paste this. No, it probably won't let me. All right. So again, let's just multiply that. So let's just write right here. MF is equal to 0.001036. And this is the little v is basically specific volume. It's meters cubed per kilogram. And little g, or v, so little g is equal to 2.3593. Okay. Meters cubed per kilogram. Hold on a second, guys. I just want to make sure I got. Okay. I don't know why I'm glowing and my icon's glowing here. I thought maybe someone's trying to. Yesterday in my other section, there was people that were in the lobby. So we have a lobby, and I had to let them in. And it's people that are guests. And what happened is I restructured the permission. So now that if you're not a part of the team, you had to be let in, and so there was people waiting in the lobby and on Discord. They were like, "Hey, let us in." And so, but I turned off that feature for this class, so no one should be. But I was still worried about that. All right, so we got the table values there that I just showed you. So therefore, now we just calculate our total volume, because MF and MG, right? Those are up here. So we have the total volume is equal to MF, which is the mass of the liquid, which is 8 kilograms. Yeah. And then V sub F is, we just wrote it down, 0.001036, plus mass of the vapor, which is 2 kilograms, times V sub G, 2.3593. So you do the calculation, and you got a total mass of 4.73 meters cubed. All right. Okay, good. All right, very good. Now let's look at the next. Let's look at the slides. Any questions on that? Hopefully that was pretty straightforward.
That was total volume, right?
Yeah.
Okay.
Exactly, total volume. Yeah. And so the problem, you have to be careful because it says find the volume of the tank. So it's not saying find the volume of the liquid. It's not saying find the volume of the gas. It's the total tank. And so therefore you have to be able to calculate the total volume. Okay. Just look out for things like that so you don't get tricked. Let's go ahead and do another. All right, the next example problem is 3 dash. This is example. That was the first one was example 3-4 in your book. This one is example 3-5. So I go from the book because this way you can refer back to the book. But once we get going, I have no problems going into the. I have extra problems that we can do, or even I can get you going on the homework. But this is kind of just the way traditionally I do it. So let's go ahead and read the next problem here. It says properties of a saturated liquid vapor mixture. So now this is a mixture problem. AKA we're going to use the quality index, which is X, right? It says an 80 liter vessel. So we're given that this is we were given that the total volume is equal to 80 liters. An 80 liter vessel contains 4 kilograms of refrigerant 134A at a pressure of 160 kilopascal. So we got refrigerant 134A at 160 kilopascals, and it's 4 kilograms. So this is total mass. They're not telling us this is the mass of a liquid or the vapor. So they're giving us the total mass. So we got that the total mass there, MT, is equal to 4 kilograms. Determine the temperature, and so determine A, the temperature, B, the quality, and C, the enthalpy of the refrigerant. So find A, temperature, B, the quality index, X, and C is the enthalpy. That's H of the refrigerant. I haven't explained what H is yet, but it's, regardless, we can learn how to find it, and then I'll explain it to you in, I believe, this lecture. If not, the next lecture. I have to look at when we start talking about. I think we already talked about H. No, maybe not. Anyway, let's not jump the gun here. All right, so that's what we're going to find. Yeah, go ahead.
Is that H just a regular H, not the Greek letter, right?
Right. Yeah, it's just I drank too much coffee, so it's
Just the regular H?
Yeah.
Okay.
Yeah, just H. So this is called enthalpy. All right. So it's basically energy content of this tank. That's what it's asking you to find. All right. So let's go ahead and again it says now this is a mixture, therefore it is saturated. So we have the fact that this is a saturated mixture. Because mixture means it's going to have a little bit of some vapor and some liquid, and therefore and it's a saturated mixture. Therefore, we can use our tables at A4 and A5. So we know where to go, where to get the information. Okay. Now let's find. I think we're going to need to find what we call the average, but we don't really use the average indicator at the bottom. We just call it specific volume. The fact that it doesn't have an F or a G implies that this is just the specific volume of that point of this tank. And then it will mean that we need to at some point find VF and VG, but we're just going to call it V from here on out, and then we're going to drop the AVG little indicator there. And so we need to find that. So we have the total volume, so therefore it's the total volume divided by, and we have the total mass. And you'll see, you may not see T used for total. So if you see mass, you have to assume it's not just the MF or mg, mass of the liquid, mass of the vapor. It's just the total mass of that system. So there we can calculate our specific volume of that tank is equal to, again, it's 80 liters. So 80 liters is the same thing as 0.80 meters cubed, because it's 1,000 liters. It's 1,000 liters in a meters cubed, and then divided by the total mass is 4 kilograms. Right. And this is equal to 0.02. 0.02 meters cubed per kilogram. All right. Now we're given that the pressure, so we haven't found the temperature yet, but we know the pressure, right? Pressure is equal to 160 kilopascal. So this gives us a golden opportunity now. Now the fact that we're given pressure, we don't use the same table as we did last time. We actually use the next table over. We use table A5. So use table, we're going to use, which is the table you use when you're given pressure. When you're given the pressure, let's see, go ahead. Boom. All right, so this was A4. We're done with this table. We got to go to A5. Here we go, A5, because on the left hand, the first column is pressure. And we're given a nice round number for this pressure. So it's a nightmare if you're, I did this basically in punishment, I guess, for one of my classes. I said, look, I'm only going to give you table A4. Actually, I gave them I didn't have table A5 with me, so they had to use table A4. And I said, you have to look up 160 kilopascal. And then if you use table A4 for that, just look up 160 kilopascal. There is no 100. There's 143 and 169, which means that they had to interpolate, right, to get the values. So these, in other words, they couldn't just grab them right off of the table. You have to kind of interpolate all these values here. And so we will do a little bit of interpolation here, how to do a quick linear interpolation. But that's why you love this next table here, because for this next table you don't have to interpolate. You just go right to, it's in nice increments of 5, and you go to 160. And they don't have 160 here. How funny. All right, that's interesting. They got 150 and they have 175. Oh, you know what? This is water. Okay, so I made a mistake. This is not water, right? We go back to the problem. Again, I mean, we can do the problem. It's just funny because they would give you an example problem and force you to do interpolation. So this is R134A. This is the stuff that's inside the air conditioner in your car, right? So that when you start losing cooling ability, it's probably because the stuff's leaking out. And you got to go get it recharged. So, all right, so that's a different table. That's not, I was looking at the water, saturated water. So that's a table way in the A, I think it's A13. So let's just go down. See here, these are the curves. If you want to, for those that want to do these problems without tables and look at these old-fashioned curves instead, and you're welcome to do that. Here we go. Saturated, so it's actually A11 is the temperature one, but we want the pressure one, so it's A12. A11, A12. I have to go update the notes right now. All right, so yeah, lo and behold, they do have, they have 160 here. All right, so this is the column that we're interested in. And we're interested in enthalpy as well, so I'm going to extend it all the way down to encompass, but I'm going to stop short of entropy because we don't want that. All right, so we want so right here we can find the pressure, right? So sorry, temperature. We were asked to find the temperature. All right, so we were asked, so it's minus 15.60 is the temperature. So if you have R134A at 160 kilopascal, which is 101.3 is atmospheric, so it's compressed refrigerant, then this is the temperature of that refrigerant. Okay, it's 15.60, minus 15.60. So let's go ahead and do that. So this is not right. This is for water. So it's actually 12. All right. And so we have okay, we found the temperature. The temperature associated with this pressure is equal to minus 15.60 degrees Celsius. All right, so that's one of the things we needed to solve. All right. Now the next one is we need to solve we need to find X. So so this is called saturated temperature or saturation temperature. That's what this T is. All right, now we need to find the quality. All right, so for the quality, we're going to need to find what V sub F is and what V sub G is. All right, so let's go back to our table. V sub F is 307435. 307435. Meters cubed per kilogram. And then VG is equal to, it's 0.12355. Meters cubed per kg. All right, so this is going to help you. So this is already, actually, I didn't realize I had these right here. So I'm looking at the table. I guess these notes were written for a section previous to section. I believe I downloaded the most recent notes, so they probably haven't updated their notes. But notice how they have V sub G here as 0.12348, and I have it here as 0.12355. So that's those. That deviation there is not important. All right, I don't go down to that kind of level of accuracy, and I understand these tables, and you can go, I mean, you can go online and websites and pick up these values, and they might be a little bit different, but they're not going to be that much different, right? They're going to, maybe the last two digits will vary, but it just shows you that. So this one's 0.00047437, and this is 7435. So yeah, there's going to be a little bit of variation, but that's okay. I won't. I'm usually looking for much coarser type of, 2 decimal figures type of accuracy. Okay, not 5, 6 decimal figures. All right, so now let's go ahead and find. All right, so the other thing is we need to find V sub FG. So V sub FG, you can calculate it. It's V sub G minus V sub F. Right, and so that turns out to be, but sometimes it's given to you in a table. So let's see if it's in the table. Just want to show you. Let's go ahead. And in this case, it's not. So there is no V sub. It would be right here in this. That would be a column right there. Notice that the other properties are calculated for you, though it's real simple just to go to grab. For example, U of FG is just basically U of G 209 minus 3.795 is 205.38. It's very simple but it's, and you're in an exam and you want to minimize how often you have to go to your calculator. This is kind of cool. But in this case, for specific volume, they don't calculate it. So I'm going to do it for us. 3.5.
0.1226065.
Okay, let's go. Okay, thank you. Let me go back then. What was it again?
It was 0.1226065.
Okay. So yeah, thank you. That is the yeah. Let me go ahead and make some more room. So you'll have to calculate that. And now why we needed all those is we need to go ahead and do this and to calculate the x. So x, the equality exponent is equal to v minus vf over v sub fg. Right. So it turns out that this is equal to v of f, right? It's 0.02. We actually came up with that value minus. That's long. Here, let me get some more room here. All right, so this is 0.0007435, right? Divided by, and then 0.1226. I'll just go to 4 decimal places, and x is equal to. Can you calculate that for me? If not, I'll do it. 0.0007435 minus. All right, so that should be 0.157, and I have it. All right, this is 0.157. So that's our quality. So think about that. This is the mass of the vapor over the total mass. So it's 15%. So it's about 16% vapor. So it's mostly liquid. So if you look at this tank here, I mean it's hard to tell because obviously the density of liquid is much higher than the density of vapor, but the overwhelming majority, about 85% of this stuff is in liquid form. Okay, that's what that quality tells us. All right, so now we just want to find the enthalpy. So now we got quality, we can find everything. So the enthalpy is, let me see if I can go ahead and just write down here. So I'm going to write it over here. The enthalpy is equal to H is equal to HF plus X times HFG. So for that, we need to go, and these are table values again. These you find in table A-12. So I'll let you do that. I'm just going to write it down. HF is equal to 31.18, 31.18, and that is kilojoules per kilogram. plus, and then we have our x 0.157 times hg. Oh no, this is hfg. Sorry, which is the table value. It's 20. We were just looking. I think we're just looking at 209.96. And then the units for that is kilojoules per kilogram as well. So we got an HGF, a total H enthalpy of 64.1 kilojoules per kilogram.
And what does that H mean again? I mean, like, what is
yeah. So this is the enthalpy of that tank. So it is the energy content. This is the enthalpy.
Okay. Energy content.
Yeah, it's basically it's the energy content.
Like a potential energy content? Or
It's everything. It includes potential as well. So it's your no, we'll describe it more. It's actually, no, I take that back. It's the thermal energy content plus the pressure. So it includes the pressure because it's in other words, if you to reach that state, like if there was zero energy, if it started off at a zero energy content, you would have to heat it up. You'd have to put 64.1 kilojoules per kilogram to reach the state. That's kind of what it's saying of heat.
oh, okay.
Yeah, heat or work. That's kind of, so anyway, this helps us solve things like how much power output in a car, for example, your piston chamber. Your piston chamber, you need to find your enthalpies. You got to find of each stroke, and so this is one of the ways we do it. Turbines, same thing. Turbo generators, we want to know. We know the temperature of the steam, and we can determine its energy content this way through determining its enthalpy. I thought I went over enthalpy. If I didn't, I'm gonna have to. You don't really need it for this. Is just a training so that you can know how to find, because we're gonna be using this a lot in chapters 4 and 5. This is just training for figuring out how to find enthalpies right here. Right? You need to get your total, your H, your enthalpy. You need the HF and you need your HG and you need to know HFG, and these are all table values. So you're gonna need to know usually a temperature and a pressure, and then you can use this table to find those values. So I will explain more as we get closer. Where we start really heavily using enthalpy is chapter 5. Okay. All right. Let's see how much more we got here. That's pretty much everything. Ideal gas. Let's go talk about ideal gas a little bit. All right. Ideal gas. That is here. All right. Oh, I didn't talk about superheated vapor. All right. So superheated vapor is the next is the next one over. So it's the next table over. And for example, to find this point, this is in the superheated range. So those tables are a little different, right? Those tables are made up of, so in this superheated vapor, you don't have one. So the temperature doesn't mean that you have the pressure now. The temperature and pressure are independent, right? So right here, so temperature and pressure now are independent. Sorry. So now you have the tables are a little harder to deal with because you have to have a temperature and a pressure. So a temperature will have different possibilities for pressure, and so you still the things still apply. You only need 2 data points. You need 2 independent variables. So your 2 independent variables could be, one could be temperature, one could be pressure for a superheated vapor. For saturated, you can't use temperature and pressure as your independent variables because they're dependent. So you would need, for saturated tables, saturated conditions, you would need, for example, a temperature and then like a specific volume, or a temperature or a pressure and an enthalpy or something like that to nail down which table, what entries in the table you need to go to. So superheated, let's see if there's an example in the book. this, just give me a second. So let's go ahead and look at it, and let's see if I can do an example. Where is the superheat? Okay, so sample 3.7. All right, so let's go ahead. So we got example 3-7 in your book. It says the temperature of superheated vapor. The temperature of water, so it's a superheated vapor. This is the temperature of water at a state of 0.5 megapascal and H equals to 2890 kilojoules. Or determine the temperature. So find, this is water, or let's call it steam. So the pressure of the steam is equal to 0.5 megapascal. And they give us an enthalpy value. Enthalpy value of the steam, the energy content of the steam is 2890 kilojoules per kilogram. And we need to find temperature. Find the temperature for this superheated vapor. All right, so what they do, I think it's going to be easier if I just grab the example from the. So is this it? No, maybe I have to draw it out. Darn it. Okay, I'm not great at drawing, but okay, let's just do it real quick. Here we go. All right, so let's just go look. Let's look up. This is going to be table for superheated vapor. It's basically A6. All right. There's only one. There's not a pressure temperature. There's only one table. Table A6 for superheated vapor, water, which this is. So let's go ahead and do that. Let's go and so we got to go to A6, A3. There we go. A5. A6. Okay, so we're given we were given the pressure is equal to 0.5 megapascal. So let's go. Where's our 0.5? Right here. We have a 0.5 column here, and then on the first column here are the temperatures. So you can see saturation. That's the lowest. Actually, that doesn't belong in this table, but it's used as a reference. So you can actually get this one from the saturation tables. But this is basically saying it's higher temperature than saturation, so it pushes you into the superheated range. And we're looking for. Oh yeah, it says that we were given an enthalpy of, what was it again? 2890. So it turns out that I'm going to go ahead and take a little snapshot of this. This is the part of the table that we're looking at, right? So I'm going to bring it with me to the problem that I was trying to solve here. All right. So we're trying to find T. All right. We're finding the temperature. All right. So we have we're given 0.5 megapascal. So this is the entry, and we're given H is equal to 2890. So that would be 28. This is H. Okay. Now I lost my place here. Which one is H? Which column? So it is the fourth from the left. It's this one here. So it's the fourth from the left. It's this one here. So we're given that's 2890. So it would be 2890 would be somewhere right here, right? Actually, I don't want to block the. So it's going to be somewhere between here. It's not this is where we have to use interpolation, right? So it's going to be right in this little section right here, this entry here. And therefore the temperature is going to be somewhere between 200 and 250. All right. That's the temperature of question right there. So so therefore what we do is we interpolate, right? And to do an interpolation, you say right, you basically say the temperature, you go ahead and write temperature in degrees C, and then you write over here, you put H in kilojoules per kilogram, and temperature degrees C, and you're given that 200 will give us 2855.8, 2855.8, and 250 will give us 28, sorry, 2961.0. So basically we need to find this temperature in between, right? So we got to find, this is our temperature that we need to find, and this is H, right? And it goes in here is equal to 2890. So the way you do this is you do kind of a triangle, and you say that is there a triangle feature here? Yeah, there is. Okay, so you say on the left column here on the vertical axis, right? You say this is temperature. And on the horizontal axis, you say this is H. All right. So now what you do is you go ahead and all right. So then you say so at the high temperature right here is 250, and the low temperature here is 200. So at 250, my enthalpy, but I think I have this backwards. It's my enthalpy is shoot, damn it. I have it backwards here. Let's go ahead and do damn it. All right. This is still the same stupid triangle, right? Okay. Okay. That's annoying. All right. So, damn it. All right. So the triangle is going to look something like this. Right. And so if this is your T and this is your H column, so at 200, you have an H equals to equals 2855, right? And over here is your H is equal to 2961, right? So you got this point and you got that point, right? So basically you want to find the temperature here, right, corresponds to 2890. So you're setting up a, basically a similar triangle type of situation. You got two similar triangles, and you say that the height of this triangle over the height of this triangle. So we can say, what is that? What's the height of that triangle? So it's 250 minus 200 divided by the height of that triangle, which is equal to, so it's T minus 200 is equal to the base here divided by the base there of that triangle. So is equal to the base, the large base, which is 291,961 minus 2855 divided by the little base of the base of the little triangle, which is 289 minus 2855. So then you solve for T, right? You're going to solve for that guy right there. So T in this equation, T should be equal to 216.3 degrees C. And now it's in between 200 and 250, right? So it's right here. So that's how you do it. Basically, you solve for T. Calculators kind of have that interpolation function. That's how you do a linear interpolation. Okay. So I didn't talk about ideal gas, but I'll do that since we have plenty of time before the exam. I'm going to go just start Tuesday's lecture talking about ideal gas, and we'll be done with chapter 3, and then we'll just start chapter 4 on Tuesday. At this point, if you guys have any questions, let me know. Questions or concerns or comments?
Sure, Professor.
No, thank you,
Yes, sir.
Professor.
Okay, great. So since you guys don't have any questions, you could, and if you do, just stick around. Okay, I got my office hour. I'm going to try to end my office hour at 6:50 because I have actually no. Yeah, I'll just go. We'll go for like 15 minutes because I have to be able to start my next lecture at 7. Anyway, all right, guys, have a good weekend and take it easy, and we'll see you on Tuesday.
All right, thank you, Professor. Before we leave, I have a question.
Yeah. Yes, sir.
So are we going to do a review session?
The review session will happen on the day that we were going to have the original day we were going to have the exam. So that'll be on the 24th. We'll have a review for the exam. Yeah. So if you guys, yeah. So this, if you guys don't, for those of you that came in late, we're doing the exam now. We're moving it out one lecture date, so it's now on the 29th. It's not the 24th anymore. You'll have the weekend to study. It's because we needed a week to do this chapter 3 homework, which I just assigned today. It's in Beachport. It's due. The homework for chapter 3 will be due on Thursday of next week.
Mm-hmm. Thank you so much, Professor.
You're welcome. Okay.
And have a good weekend.
All right, you too.
Hi, Professor. I got a question about chapter 2 homework.
Okay.
So it's the first question. So it's asking about the heat like coming out from the mortar. So
Yeah.
how so the heat transfer is like, is it I mean kind of like the same as like total I mean delta E equal to like energy in minus energy out. Is that right?
I guess that's one way of looking at it. So we're not really looking for so we're looking for heat of conduction, all right? So, we're looking for Q, because that was one of the things we talked in chapter for conduction, so COND. So when you have, for example, if you have, in this case, we had a brick wall, right? So with a certain thickness and an area, then what you can do is you can determine what the conduction is through that brick wall, right? By as long as you know, so that's, again, that's Q. We have an equation for that. So the equation basically is equal to, so it's equal to, it's the thermal conductivity of the material times the area divided by the distance times T, the temperature difference across the wall. I say T hot minus T cold. And I forget it was like, I forget what the temperature is inside the wall here, 20, I don't know if it was like 20 degrees, and outside it was something like like 5 degrees or something like that. Right, and then we.
I'm
right.
sorry, Professor. I was talking about the problem number 1.
Oh, this isn't problem number 1.
That is
Okay.
that is not the problem number 1.
Okay,
That is
okay.
number 3. Yeah, I was talking
All
about
right.
the 2 motor, like.
Oh, okay. I was thinking
Very
like.
first. Yeah. Yes.
Oh, the motor. Sorry, I thought you said mortar, like a brick wall.
Oh.
I accidentally. I have the same. I say the same thing. When I'm talking, I say like motorcycle. I say mortar cycle. So you say it the exact same way I do. So I confuse myself. All right. So the motor. All right. So what about the motor?
So asking about the heat coming out from the motor. So
Okay.
like what equation
Yeah.
like to put in there?
Okay. Yeah. Okay. Yeah. So for
Yes.
that one we have So we have so let me just go ahead and bear with me here. It's a little bit easier if I just do a shape here, and then so you got the motor with the shaft. All right. So what you have here is this is a 70. Now I'm going to go back to a pen. This is 70. I think it was 75 horsepower. 75.
75. Yes.
Right. But then there's an electrical input that goes into the motor that we need to know. So we call that E dot. Right. We call it, or you can call it whatever you want, but it's the energy associated with the motor. So so we have two motors that we're dealing with, right? We have an old and a new. We're going to replace it with a new motor. So therefore we have we have two efficiencies, right? The old efficient, since the efficiency of the old motor was like 91 or something like that %.
91%. Yes.
And the efficiency of the new motor is equal to like
Yes.
95 point something.
Yeah, 9.54.
54. So I'll just say 95.4%.
95.4.
All right.
Yeah.
Yeah. So again, we need now. This was, I'm going to say E dot old, and this is E dot new. Right. For the new.
There is electric input, right?
Yes, this is electric input. So
that's kind of the same as the walk and the walk energy, right? I mean, walk.
Well, it is work. You're right. Electric input is work.
Yeah. Work.
So
okay.
you could call this. You basically could call it in. Right. We can call it that too. There's nothing wrong with that. The only thing is there's two. Each motor will have 2 different work ends, and because the old one is not as efficient, so therefore it's going to need more electricity, more work to put in, more electric work than the new one. The new one is going to be more efficient, therefore it's less electric work. The output's still the same, right? We got 75 horsepower.
Yes.
On both, right? So that's a given. It's not for both. We'll have the same exact right. So then so what you need to do is I think the problem said what your question is how to set it up, because I think it said what is the, because there's heat associated. There's heat. The fact that this isn't 100%. The fact that it's 91%, therefore it's 9% non-efficient or inefficient, and that 9% of that energy that came in is going to be expelled as heat. So there's heat loss there.
Yes.
So there's a heat loss associated with the old, and there's less heat loss with the new. There's many ways of doing this, but basically what you're doing is you're the bottom line is that you need to calculate the electricity for both, the work in. And when you do that, you subtract the two, and you're able to get the heat gain, the amount of heat you're reducing that goes into the room, right? So so in other words, so you need to find, I don't know if that's, I'm going to post the solutions, but you need to basically find E dot O E dot O E dot new, right? And that'll give you, that's the change of energy, which basically manifests itself as your change in heat. This is what you're trying to find. Now, how you do that is, how do you determine that? How do you find these, right? Well, the way you find it is that how much electricity is required to run that old motor is equal to the shaft output. So it's the work of the shaft divided by the efficiency of the old motor. And the work of the shaft, this is 75 horsepower. But since you're dealing with electricity, you want to convert that to kilowatts, right? And the way you do that is you multiply. Right, there's what is it? 0.746746 kilowatts per horsepower. Right, so you convert it to kilowatts, you put it here, you divide it by 0.91, and you get an E.
Yes.
E dot O. All right, and you do the same thing for E dot new.
Yeah.
And then you subtract the two, and you find the heat. That's the best way of doing it.
Oh, first, so so I found the E dot. I mean, the O one, right? And then
Yeah.
after that, I find the QO by doing the energy in minus energy out.
Yeah, that's fine. You can do that too. You can find this, and then what? Then you found this. Do the same method and find that, and then subtract the two or something, or
The two of them, and yeah, that is
yeah,
the energy difference.
that's fine.
There's
You
a
can do
heat
it. You should get exactly the same answer. Exactly. No, that's the right way of doing it, actually. To energy in minus energy out. So you can do it that way too.
Because I thought like the delta E equal to like the whole energy system equal to like energy in minus energy out. But I didn't thought about the other. I can use that on the heat also. But the heat is also the energy also, right?
Yeah.
I mean,
Yeah, it's because energy in is equal to energy out. So yeah, either way is going to give you the right answer. So
I see, Rosa.
yeah.
There are so many ways like to solve the first question. I mean, the very first question.
Yeah.
I found 3 ways to solve it.
Oh no. Yeah. No. That's true. There's the important thing is that you get the right answer each way, and that's all that matters. So okay. All right, Kant. So does anyone have any other questions? You guys might have to email me because I have to run to my other class. I have a problem in my other class. If I don't get there, see, I think someone already started a video. Someone will start a video and everyone gets confused and runs to their video. Like, you guys can start your own video if you wanted to, and then you'll start noticing people start joining in. So I need to go start the video and post the link. So I'm gonna have to run, guys. All right.
Thank you, bro.
Okay. Edgar, Isabel, Min, and V. So if you guys need to get a hold of me, just chat with me or send me an email. Okay. You guys take care. Have a good weekend.